Hi, I'm John Quinn. I work in Google's Research Centre in Ghana and also in Uganda for the non-profit Sunbird AI and the Makerere University AI Lab. A bit of history. I've worked in Uganda for about 14 years and about 5 of those for the UN. And this is the background from which I would like to talk about the UN's global goals and what I think the computer vision community can do to make progress on them, and why we didn't already make as much progress as we might have. The global goals for sustainable development are a set of targets in the categories you see here. These are quite wide-ranging, from health to climate, all sorts of things. And what's important is that each has a set of specific measurable targets, like malaria incidents per 1,000 people. So these are a view of the major challenges and where we want the world to be by 2030. How does computer vision fit into this? I'd like to focus on 2 categories of applications. One is regarding information gaps. So it may be that information is missing, which is needed for planning or executing the goals, or ways of measuring those indicators I showed on the previous slide. And there may be some way that computer vision has a role in that. The second category is about the shortage of experts in low resource settings. By experts, doctors, agricultural extension workers, vets, midwives, and so on. What I want to do in this talk is give a few examples of applications where there's potential of these sorts, things that I happen to have been involved in, which also illustrate some of the difficulties and the limitations. So I want to talk about some of these challenges and my favorite way of mitigating these, which is community building. First example of information gaps, and this is about population density and simply knowing how many people there are. So our estimates of population come from censuses, and censuses can be surprisingly out of date. Last census in Somalia was 1975, DRC about 40 years ago. So this means that all of the numbers that we use, for example, as the indicators of these goals, which are denominated in population, like vaccination rates or GDP per capita, are actually estimates and sometimes quite loose ones. Some work that's been going on with Google Ghana and Google Switzerland is about using high-resolution satellite imagery to count buildings across the developing world. And knowing where buildings are is not quite the same as knowing where population is, but it's an important step closer and has some useful practical applications in its own right. This is a difficult problem in vision terms. So the way that landscapes and settlements look is very different across the world. There's this high diversity of colors and shapes and sizes. We also have to remember, dealing with satellite imagery, we're basically dealing with photos taken by a camera 700 or 800 kilometers away. So even this high resolution imagery, like 50 centimeter per pixel, a building could be a blob a few pixels wide. And many instances per image. We've been working on segmentation pipelines for dealing with this, quite simple ones, based on UNet, which is often used on satellite imagery, and with some modifications to make it work for this particular task. So interestingly, we find nothing really works off the shelf, and the limitations, particularly here with methods that we tried, were to do with like the very small size and high density of instances. Having trained a model to do this, we can apply it on successively larger areas to find the building footprints and eventually at the scale of whole continents. So what you see here is a count of the buildings across the continent of Africa, which is a really rich data resource. So with knowledge of where all these buildings are, this is useful for population mapping, for addressing systems for humanitarian response if there's some disaster, to know how many buildings or households there were in the affected area, climate science like modeling carbon emissions or environmental footprint. Next example of something that can be useful, if we go from that zoomed out view of the world to zooming right in to medical diagnosis, what you see here is some image capture of a blood smear showing Plasmodium, the organism that causes malaria. Access to diagnostics is an important limitation for public health worldwide. So malaria, for example, is often diagnosed symptomatically. Someone has a fever, they're prescribed malaria drugs, and this runs the risk of treating the wrong condition, of drug resistance, and the economic burden of buying drugs which aren't needed. Diagnosis is a limitation largely because of a scarcity of lab technicians, especially in rural areas. There's lots of microscopes, but not the trained staff to use them. As a result, the job is quite difficult for the few lab technicians there are. So Alfred Andama on our team is a principal lab technologist at the National Referral Hospital in Uganda, Malago, and he describes the difficulty of this task and the burden of concentration after dealing with many tests in a day. You close your eyes and see malaria parasites. Very difficult to have concentration and to keep up accuracy. So a really interesting kind of application area for computer vision. It's what we can do with malaria, we can in principle do with any visual lab test. So like tuberculosis bacilli, we've looked at intestinal parasites in stool samples. And in fact, any visual test, so like dermatology, for example. In Uganda, there's one dermatologist for roughly every 2 million people. So interesting opportunities to encode the expertise into a model. This goes for agricultural diagnosis as well. Example here of cassava, which is a very significant crop. It's one of the major human sources of carbohydrate. It's robust to drought. It's an insurance crop, so it can be grown and left in the ground for long periods and dug up when needed. But it's vulnerable to viral disease. And the team in Uganda here has been working with the National Crop Resources Research Institute for many years, digitizing the systems by which they collect images around the country and work out where the disease frontiers are for new strains. Similarly to the human diagnosis case, as we build up resources of labeled data, we can do lots of interesting diagnostic tasks. And things for survey. So what you see at the top here is data from a Kaggle competition on diagnosing different cassava diseases. It's not just the aerial parts of the plant. Crop disease survey is partly about looking at the symptoms. So this is root necrosis, which can also usefully be measured visually. And survey also involves quantifying the disease vector. So whiteflies carry some cassava diseases, and surveyors normally count these manually, which, as you might imagine, is an infuriating task. If you turn over a leaf and there's hundreds of flies moving around, and you have to count them with a clicker, 1, 2, 3. Much better to have a vision app on some device which just does the count. These possibilities I've described are scratching the surface. There's all sorts of really interesting work by many teams on prototypes and larger scale systems in all of these things. Other aspects of health, veterinary diagnostics, people working on remote sensing for economic indicators. This idea of counterfeit drug detection, just an illustration here of genuine drug packaging and a counterfeit. So lots of possibilities to address these global challenges. However, I'm now going to disappoint you because it's quite difficult to get these to work in practice. And in fact, despite many teams working on many promising ideas, there are very few computer vision or machine learning based systems in real use in the developing world. So why is that? Firstly, technical factors. There are quite strong constraints on deployment. Looking at the global situation, access to power, to network, compute and memory resources. If we are to develop systems which work, for example, on the world's 3 billion smartphones, they have to be quite parsimonious in terms of model size and so on. So, side note, the field of computer vision has put some focus on increasingly large models with increasingly good performance, but often what we need is portable models which are more easily deployable. It may be necessary to build things end to end, so to own the whole process from collecting the data to developing the model, creating the app, the UX, getting the buy-in from the relevant authorities, for the reason that if something is really new, then nobody else might pick up one of these other links. As a result, the timescales can be quite long. There can be projects in this kind of context which go on for 10 years or more. It may outlast the runway of a startup or the time available to a particular team. And maintenance and sustainability are a big part of this, getting something to a situation where it supports its own weight. And there's a large kind of scrap heap of projects which seem to be good ideas in principle, but didn't really get to that self-supporting stage, of which I've certainly contributed my fair share. Human factors. First thing I'd like to point out is the difficulty of identifying the right problem for a team working at a distance, geographically or culturally. I think in problem identification, it's important to have a team who live the problem and understands the nuances and the subtleties. So part of this is finding the right metric. The global goals have some metrics defined. It may be necessary to go into a level more precise metrics, but also in computer vision terms, things like the labeling policy, where this really helps to understand all the subtleties of the context. Simple example of the building detection problem I described. Detecting roofs seems like a simple thing to label, and we might choose not to label walls or construction sites. But this is a context where people often build a building floor by floor, start using one story as the rest is left open. So the labeling policy and the people rating the images have to know how to do that. So this point applies, I think, at problem definition and dataset collection stage. Once that's done and the metrics defined and there's datasets, then I think this is wide open and other teams from anywhere can contribute. Secondly, the requirement for organizational work versus machine learning, which can be burdensome and not particularly well incentivized. So an example here of some work by my former PhD student, Rose Nachibule at Makerere, who was working on low-cost traffic monitoring systems in Kampala. And much of the time taken in her work was simply obtaining permission from the authorities to mount a mysterious box of electronics to a lamppost. Trust amongst collaborators and domain experts is important to have the means of deploying and, where relevant, getting the inside knowledge on working practices or data sets and their limitations, things which may not be publicly known, but it's important to know how things are in practice. Particularly, this is the case when dealing with datasets, published datasets, and how they were really put together. To adapt an old saying, global development statistics are a bit like sausages in that your confidence in them goes down the more you understand how they're put together. Some ways that deficit in trust can manifest are it could appear the same as bureaucracy. So sometimes people may experience frustration with an NGO or a government ministry that they aren't approving or supporting something in a timely manner. But the underlying problem may be that they're not sufficiently bought into the benefits and may have to face any unintended consequences, which we'll discuss later. Another way that lack of confidence can manifest, if something, for example, is a machine learning based system that provides some kind of analysis, showing it to a domain expert who might come back with one of two responses. One, the system showed me what I expected, therefore it's not useful. Or two, this system showed me what I didn't expect, therefore it's wrong. And the underlying problem is a kind of basic lack of trust or confidence, which has to be built up. So the worst case scenario, I believe, is not just that systems don't work, but that they actually cause harm. As researchers, we are trained and incentivized to look at the upside and not the knock-on effects. But this is a natural idea in machine learning. We're used to optimizing one performance metric at the expense of others. And the global goals themselves are kind of anti-correlated. For example, you could use natural resources, consume them to pay for education and healthcare. In terms of introducing technology or machine learning technology, one thing I'd like to highlight is inequality and how that can be reinforced by technology. Anything we do which is technological as a solution to a problem will be most easily accessed by those already at a high technology level. Those who have the electricity, the network, the devices to be able to access it, and the gap might further increase between those who don't. Related to this is if a system is successful and it becomes the new way of doing things. For example, if malaria diagnosis was always done by an app on a network, then this creates a risk that when the network or the power goes off, then maybe people don't have access to diagnosis. It creates some new fragility. Pilotitis is a term, I believe, coined by my former colleague Sean Blaschke, who explained that Uganda is experiencing a new outbreak. We have an epidemic of digital health systems. These are systems where people are collecting data and running apps in parallel, and it's a state of discordant proliferation. Many of these will subsequently be abandoned. And as I mentioned before, the time of experts is a scarce resource, and this runs the risk of using up people's time to the detriment of others. About new technology and new ethical issues, I think other people are better able than me to talk about like biases encoded in computer vision systems. I'd like to make a point about unintended uses of systems we create while enabling application A. Maybe we unintentionally enable B, C, and D that we didn't think about. An example of this is humanitarian relief operations share some practical characteristics with military operations. So I think it's important to be intentional about what we enable with new technology. Sometimes the unintended consequences are positive. We found with the cassava diagnosis work that our trial participants were able to make money by renting out their phones with diagnosis apps to other farmers, unintended revenue streams we hadn't really thought of. So these are some of the problems and the risks of using computer vision to address global challenges. My favorite way to deal with these is with the building of local communities. And in general, a wider group has some staying power. It can outlast an individual or a single team. it's a source of realistic local grounding, contacts, and understanding of the nuances and the subtleties, what's involved in really getting something to work and what might the risks be. A community I would particularly want to spotlight is Data Science Africa, which I enjoy very much. This started as a machine learning summer school in Uganda, and became what I would describe as a mutual support society. It's kind of training plus research networking. These are exciting events, and often the session which generates the most excitement is embedded hardware or Internet of Things. And I think when we talk about computer vision with low power and compute and cost requirements, then the possibilities really come alive for this audience. One observation about things which emerged in this community is this end-to-end theme really keeps being repeated. A single team has to own everything from dataset collection up to facilitating the use of the end product and promoting it. And we're now experimenting with country-level groups. So we have like a Uganda chapter, which are fascinating meetings. You have people from government and academia and business, all kind of motivated by curiosity and a sense of the possibilities. So these are groups who know the priority problems in society, also the technological opportunity. They're under no illusions about the complexity of implementing it and what the consequences might be. Some other recent events closer to CVPR, there was this nice Computer Vision for Global Challenges workshop, a map here of where the participants came from. So this is really nice for enriching the body of researchers, the computer vision field. I think two advantages of this. One is that computer vision research is then able to be inspired by what are the major problems worldwide, and also there's a route for new technological solutions to get back into the world. Computer Vision for Agriculture was another nice event. So some thoughts to wrap up. How to get involved, even for people who work only on methodology. Methodology is still grounded by particular canonical problems or data sets. One possibility is choosing extra benchmarks, in remote sensing or medical imaging. Also to consider models which are widely accessible worldwide, like ones with fewer like compute or memory requirements. More in depth is to do with cross-disciplinary collaboration and community formation. I think everyone is local to somewhere, and these are global problems. And I think one advantage there is that the constraints of real-world problems can often be inspiring for new methodology. Finally, I think interesting problems are everywhere, so there's a great deal of potential. That concludes the talk. Thank you for listening.